Right, by the use of definition, prove that the limit of z bar as z approaches z0 is z bar of 0, or z0 bar. Second Roman figure, the limit as z tends to 0, or z bar squared divided by z equals 0. You need to use the definition to prove this and the rest of this. So we proceed now to solve each of these questions in detail. But first, we're going to use the definition for 1a, 1 Roman figure 1, Roman figure 2, Roman figure 3. So let's proceed. Let us proceed. Right, so now in view of this one here, using the definition, using the definition, to prove, we proceed as follows, and we say given epsilon positive, we must find delta positive such that if 0 is less than the modulus of z minus z sub 0, less than delta, then the modulus of z bar minus z naught bar is less than epsilon. Now, with this said, thus we have the following. So we have that. Now we begin by focusing on this part here. So we then say with that part, z bar minus z naught bar, which is the complex conjugate of z, the complex conjugate of z naught. And we know very well that this is exactly the same. And so the complex conjugate, now the difference of complex conjugates can be seen and is known to be exactly the complex conjugate of the difference. So to be the complex conjugate of the difference like so. And from this, we know that this is exactly the same as the modulus of the complex conjugate is the same as the modulus of the complex number without the complex conjugate. Hence delta is exactly the same as epsilon. Okay. Delta is exactly the same as epsilon. So we proceed to look at the next thing. Right, in view of this one here, so here we need to prove that this one here first, things first. So we need to prove that this one equals 0. Okay, because that is what this says. We need to prove that this limit equals 0. And we proceed to prove this. So by using the definition, given epsilon positive, we must find delta positive. Let's find delta positive such that if 0 such that if, now we focus on this one, z minus 0 is less than delta, then the modulus of the function z bar squared divided by z is less than epsilon. So with that said, thus we proceed to have the following. So now we're going to focus on this part, which is z bar squared which is z bar minus naught. Okay. And what is this? This can exactly be seen as follows. What is this? So this is exactly the same as z bar squared divided by z. Okay, now we divide these by that, which is that. In which case, therefore, this is exactly this. And this is less than epsilon. Hence, by comparison, because we know that the modulus of z from here is less than delta, the modulus of z is less than epsilon here. Hence, delta equals epsilon. Okay. Proceed to look at the next one. Now we need to prove this here as well by using the definition. By using the definition. Okay, we start by saying given epsilon positive, we must find delta positive such that if 0 is less than z minus z0 less than delta, then the real part of z minus the real part of z0 is less than epsilon. Thus, now, at this point, what we do, we analyze this very, very carefully. Thus, given the modulus of the real part of z minus the real part of z0, okay, this is the modulus of the real part, z minus z0. Okay, so this is less than or equal to z minus z0. And now this here, the modulus of z minus z0 is less than delta. Hence, since the modulus of z minus z0, that modulus is less than delta, we can safely say that hence delta equals epsilon for this particular question. Next. Okay, so here, what we're supposed to do, we remember the instruction. So in the second part, we just need to find the limits. For finding the limit here. Finding the limits. Okay. If the limit is z approaches z naught, 1 over z to the power n, which is the limit is z approaches z naught of 1 divided by the limit is z approaches z naught of z to the power n. And this is 1 divided by z naught to the power n. Okay, so we have now we use the quotient rule of the limit here. So in the end, we say hence the limit is z approaches z sub naught of 1 over z to the n is z naught to the n. Okay, so yeah, that's what we have. Right, we focus now on the next one. This particular one. So we need to find the limit. So finding the limit. Finding the limit. Right. If the limit is z approaches I z cubed minus 1 divided by this. All right, now look at these carefully. Take the limit here, z approaches that. You cube this. Okay, so if you cube this is minus I. Okay, in which case it's 1 minus 1. Which is 0 over 2I. And this is 0. And this is 0. Hence the limit as z approaches the complex number I, or the imaginary number, I being a purely imaginary number, z plus I, it follows therefore that this limit is 0. This limit is identically 0. Okay, and therefore we're done with this one. Like so. We're done. So now we now thank everybody and a goodbye to you.